Hello students, how are you? Today I am going to discuss another important concept uh, to understand nucleophilic substitution reaction. This important concept is nucleophilicity, that is effect of entering group, because in nucleophilic substitution reaction there is a very important role of nucleophile. And the term nucleophilicity is considered to be the ability of a Lewis base to act as a nucleophile and is measured by the relative rate of nucleophilic substitution reaction of different nucleophile with common substrate. Okay, so actually here basically nucleophile and base. Nucleophile and base are quite similar but not always. They are not always similar, nucleophile and base. Yes, both contains negatively charged, okay, or both contains lone pairs, but always they are not same. Qualitatively, this concept is related to Lewis basicity, but sometimes a conflict between the two may arise. So, nucleophilicity and basicity are not always similar. Is that clear? Basicity is defined in terms of the position of an equilibrium reaction with proton usually. If we consider Bronsted-Lowry concept, okay, means acceptor is base and proton donor is acid. Therefore, while nucleophilicity is used to describe trends in the kinetic aspect of reaction, basicity is related to the thermodynamics, because I just told you basicity is defined in terms of position of an equilibrium. Equilibrium reaction with a proton usually. Suppose HA, it's acid, base. If HA is a strong acid, then this equilibrium will be shifted towards right hand side. But when I am talking about nucleophilicity, actually nucleophile has a very unique property in organic chemistry. It has a connection with carbon center. Clear? It has a connection with carbon center, not H plus. Base has a connection with H plus. Base uh, takes up H plus, but nucleophile makes bond with carbon, not H plus. That is the main very basic difference between nucleophilicity and basicity. Base has a connection with H plus, but nucleophile has a connection with C delta plus. This is the very basic difference between basicity and nucleophilicity. And another thing, just I told you that nucleophilicity adheres to reaction rate. Reaction rate means reaction kinetics, but base has a connection with reaction equilibrium, means it has a connection with thermodynamics. Is that clear? So this is the basic difference between basicity and nucleophilicity. And again I am telling you that please try to watch the whole video. You will get some very unique concepts on nucleophilicity and basicity, because these two terms sometimes they are in a conflict. Always they are not same. Always they don't run in a same track. Clear? And with a good nucleophile, the rate of SN2 reaction will increase. Good nucleophile rate of SN2 reaction increase. And with a good nucleophile, there may be a changeover in the reaction pathway from SN1 to SN2. If good nucleophile, then SN1, there may be a changeover between SN1 to SN2 reaction. Clear? So the thumb rule that higher the basicity, higher is the nucleophilicity. If when we have the same nucleophilic center, that is very important. The first thing is that the thumb rule, the higher the basicity, higher is the nucleophilicity. It is true if we have the same nucleophilic center, that is the same donor atom. Okay. So higher the basicity, higher will be the nucleophilicity if attacking or donor atoms are same. Thus, CH3 CH2 O minus, PHO minus, H3C acetate ion, this is phenoxide ion, and nitrate ion. Here, on moving from left to right, nucleophilicity decreases and basicity also decreases, because here attacking center, attacking our donor atoms are same, so nucleophilicity and basicity run in a same order, run in a same track. See here, in the first example, that is in ethoxide ion, negative charge is concentrated on oxygen atom, so it has high basicity because it tries to be neutral. So that is why according to basicity, it wants to react with H plus to become neutral. In case of in terms of nucleophilicity, it it has a high tendency to attack C delta positive charge species, C delta positive center. Okay, but here basicity is low because negative charge is dispersed over the benzene ring through resonance. Here also through resonance, negative charge dispersed over these two oxygen atom. Here also negative charge is dispersed over free oxygen atom through resonance. But here no resonance is possible. Negative charge is concentrated on the oxygen atom, this oxygen atom. So that is why here basicity is very high, and as attacking atoms are same, so basicity and nucleophilicity run in a same track. Is that clear? Next point is, a nucleophile with a negative charge always has a higher nucleophilicity than the corresponding conjugate acid, or I can say than the corresponding neutral species. Clear? Assuming that the neutral species or conjugate acid are also nucleophile. For example, I am giving you HO minus and H2. See, here also the attacking centers are same, that is oxygen atom. Obviously, basicity of HO minus is higher than that of water. Clear? So that is why basicity is higher. Basicity of HO minus is higher than that of H2, as attacking or donor atoms are same. So basicity and nucleophilicity run in the same order. So HO minus has higher nucleophilicity than that of water molecule. So basicity and nucleophilicity run in a same order. This is the order of basicity and nucleophilicity. In a similar way, NH2 minus is more nucleophilic or more basic than NH3, corresponding neutral state, And or I can say this is the NH3 is the conjugate acid of NH NH2 NH2 minus. Conjugate acid means whenever you will try to get the conjugate acid, then add H plus. If you add H plus to NH2 minus, then you will get NH3. So this is conjugate acid, this is corresponding base. And assuming NH2 minus and NH3 both are nucleophile, but charged species, negatively charged species, will be more nucleophilic than that of its neutral form. Clear? Next point is that in comparing nucleophiles whose attacking atom in the same row of periodic table, yes, same row of periodic table, then also nucleophilicity is approximately in the order of basicity. Obviously, I need to give you an example. Suppose R3C minus, R2N minus, RO minus, F minus. Here, carbon, nitrogen, oxygen, fluorine, all are in the same row of the periodic table, that is row 2. Clear? Just try to remind the periodic table, then you will get the answer, then you will understand. Carbon, nitrogen, oxygen, fluorine, they are in the same row of the periodic table. And I am telling you, here also basicity and nucleophilicity are same, they run in a same track. If basicity increases, then nucleophilicity also increases. In this example, on moving from left to right, basicity and nucleophilicity decrease. Now, obviously, you are thinking why? This is very simple. Just try to remind the electronegativity. Fluorine has the maximum electronegativity, and carbon has the minimum electronegativity. Here carbon has the minimum tendency to hold the electron pair. So R3C minus becomes very, very unstable, because it has like nearly zero tendency to hold the electron pair, because it has least in this series carbon has minimum electronegativity. So it has very less tendency to hold the electron pair. As a result, it becomes very unstable. So it wants to react with H plus to become neutral. That is why R3C minus has the highest basicity in this series, and as F fluorine has the highest electronegativity, so it can hold it has a high tendency to hold the electron pair. So F minus is to some extent in this series, F minus is the highest, it has the highest stability among the all anions. Clear? Is that clear? So that is why F minus the least basic, and R3C minus has it is the basicity of R3C minus is the highest one. Maximum basicity is R3C minus. So nucleophilicity of R3C minus is maximum, and nucleophilicity of F minus is minimum in this series, because here basicity and nucleophilicity run in a same track. Obviously, how I'm describing the basicity, I will describe in the videos on acid base. Or clear? Obviously, I'll make a video on this. Another important concept: metal hydride. You know, lithium hydride, sodium hydride. These are called metal hydride because lithium, sodium, these are metal. So here, lithium plus H minus, sodium plus H minus. These H minus, are very poor nucleophile. But hydride, complex metal hydride such as lithium aluminium hydride, sodium borohydride, they are actually good nucleophile. Why? Because nucleophilicity, this is very unique concept. It has a directional character. Yes, nucleophile has a directional character. Clear? But in hydride from lithium hydride and sodium hydride, they don't have any directional character. These are only pure 1s orbital. 1s orbital contains 2 electrons. But here in lithium plus AlH4 minus, this is the structural hybridization of AlH4 minus. And here aluminium is sp3 hybridized. As aluminium is sp3 hybridized, so 1s orbital of hydrogen makes bond with sp3 orbital, sp3 hybridized orbital. So as a result, this hydride gets some directional character because it makes there is an overlap between sp3 and 1s orbital. So that is why this hydride gets some directional character, and due to this, hydride of complex that is why complex metal hydrides are good nucleophile because it gets some directional character. Is that clear? So the higher nucleophilicity of complex metal hydrides is attributed to the directional character of metal H bonds, for which it can attack the carbon electrophile from the further away, and the extent of overlap with orbital of the carbon undergoing nucleophilic attack is higher. I am giving you an example. Suppose this is simple alkyl halide. This is aluminium hydride. See, this hydride from this complex attacks the electrophilic center. Then obviously we are expecting a new bond between hydrogen, this, and carbon. This is simple SN2 reaction via SN2, and it's a very unique process to get the alkane from alkyl halide. Now I'm going to give you another very unique concept. Very unique concept. Okay, let's learn this unique concept. Always, positively charged species has higher energy than that of negatively charged species. In organic chemistry, most of the reaction is ionic mechanism, means positively charged makes bond with a negatively charged species. This is the organic chemistry. If you are able to understand this bond making process, then you will be boss in organic chemistry. you will be boss in organic reaction mechanism. Believe me. Okay, try to understand the bond making and bond breaking process. And if the energy difference between positively charged species and negatively charged species is small, then there will be very good bonding. Yes, and the probability of bonding will be high. And if the energy difference between positively charged species and the negatively charged species is high, then the possibility of bonding will be less. Suppose this is C delta plus, and this is the energetically the position of the C delta plus is here. Okay, and nucleophile or base. Suppose here I am talking about nucleophile. So any nucleophile, suppose HO minus, uh, the energetic position of HO minus is here. Okay, and then what will be the position of, in this diagram, what will be the position of HOO minus? Or yes, suppose here just try to understand what is the position of HOO minus. Can you tell me whether the energy of HO minus will be higher or lower than that of HO minus? This HO minus has come from hydrogen peroxide. Okay, it has come from hydrogen peroxide. After deprotonation of any hydrogen, you will get HO minus. Actually, the energy of HO minus will be higher than HO minus. Now why? Because HOO minus, here 3 non-bonded electron pair. In oxygen also it has 2 non-bonded electron. So due to lone pair repulsion, the energy of HOO minus will be higher than that of HO minus, because in HO minus there will be no lone pair repulsion. Now think, energy difference between C delta plus and HOO minus, and energy difference between C delta plus and HO minus, which is higher? Obviously energy difference between C delta plus and HO minus is higher than that of C delta plus and HO minus. So possibility of bonding will be higher between C delta plus and HO minus. According to this data, I can say that HOO minus is more nucleophilic than that of HO minus. Clear? In a similar way, try to do it by yourself. Try to draw this energetic diagram by yourself. NH3 and NH2. In NH2 also you will have lone pair repulsion, but in NH3 there is no lone pair repulsion. So that is why NH2, this hydrogen is more nucleophilic than that of ammonia. It can be explained from molecular orbital theory, but here I am not going to explain this through molecular orbital concept of molecular orbital. Just I am trying to explain you from the concept of valence bond theory, lone pair repulsion. Okay, and this is called alpha effect. This phenomenon is called alpha effect, and due to alpha effect, HOO minus is more nucleophilic than HO minus, and hydrogen is more nucleophilic than ammonia. Clear? Basicity and nucleophilicity differ on an important point. Basicity is commonly related to an attachment of H plus. Already I told you basicity is commonly related to an attachment with H plus. H plus is a very small, and in the small and H plus is very small where 1 unit positive charge is present. So you can say positive charge density on H plus is very high. So we can consider it as a hard acidic center. Clear? But C delta plus, carbon is comparatively larger than hydrogen, and here delta positive charge is present, not full positive charge is present on carbon atom. Delta positive charge is present, partial positive charge is present on carbon atom. So positive charge density on carbon atom is relatively smaller than that of H plus. So we can consider it as a soft acidic center. Clear? And if a suppose HO minus and consider RS minus. Here negative charge is on oxygen atom, and here negative charge is on sulfur atom. And we know that size of sulfur is higher than that of oxygen. So 1 unit negative charge is present on sulfur atom and 1 unit negative charge is present on oxygen atom in HO minus. As sulfur is larger than that of oxygen, so you can say the negative charge density is lower in RS minus than that of in HO minus. So that is why RS minus can be considered as soft basic center, soft base, or sulfur is soft basic center, and heat is HO minus, you can consider it as a hard base, or here oxygen is hard basic center. And always in chemistry, soft prefers soft acid prefers soft base, and hard acid prefers hard base. So that is why this interaction is preferred, not this interaction. Similarly, this interaction is preferred, but not this interaction. Hard soft is not preferred, soft is preferred. So according to this concept, you can say that RS minus is more nucleophilic than RO minus, or yes, in the here I can consider this is RO minus. Okay, RS minus is more nucleophilic than RO minus. Similar way, I minus is more nucleophilic than Br minus, and Br minus is more nucleophilic than Cl minus. Is that clear? If from this data, from this concept, we can conclude that if attacking or donor atoms are in a same group in a periodic table, then on moving from top to bottom, order of nucleophilicity increases. Basicity decreases, but nucleophilicity increases. Obviously, oxygen and sulfur are in the same group. Here, RO minus is good base, but RS minus is bad base. But RO minus is bad nucleophile, but RS minus is good nucleophile. I think now concept is clear. Again, I am telling you that if attacking or donor atom are in the same group of a periodic table, then on moving from top to bottom, nucleophilicity increases, basicity decreases. Here, nucleophilicity and basicity do not run in a same track. Okay? I think it is clear. So now, I'm going to give you a very good example. I think after that, your concept will be more clear. Rx any alkyl halide, I'm considered Rx is a primary alkyl halide, okay, and you are treating this primary alkyl halide with ethanolic cation. In that case, product is alkyl cyanide. But if you treat Rx with AgCN, solvent is ether, then product is alkyl isocyanide. We are getting completely different product. Why? Yes, why? Very very typical examples. Okay, KCN, you are getting one product. If you after treating it with AgCN, you are getting different one. Okay, let us try to explain this observation. Obviously, CN minus can act as an ambident nucleophile. What do you mean by ambident nucleophile? Means it can attack through both end, from carbon end, from nitrogen end. But carbon is less electronegative, okay, less electronegative center, so it is softer, okay, and obviously carbon is larger than that of nitrogen, so in negative charge relation carbon is lesser than that of nitrogen, so we can consider it as a soft end, soft basic center. But nitrogen is more electronegative and it is smaller than that of carbon, so we can consider it as a hard basic center. And soft basic center loves soft acidic center and hard basic center loves hard acidic center. Okay, now Rx, delta plus, delta minus, suppose it is CH3. Okay, I'm considering it as a CH3, CH3X. This is delta plus, this is delta minus, and carbon is soft acidic center. Okay, because partial positive charge is present on carbon atom. So it is likely that attack will be from carbon end. Then you will get CH3 CN. Clear? But in case of when cyanide is coming from KCN. Okay. But what happens if cyanide is coming from AgCN? Let's see. CH3X, and I'm considering X is iodine. CH3I means methyl iodide. Okay, Ag plus. Iodine, very large atom, and on iodine there are 3 lone pair. So large atom and it has 3 lone pairs, but iodine is larger than bromine. Okay, so iodine is a very large atom. So we can consider it as a soft basic center. Similarly, silver ion, large silver is large atom and one unit positive charge is present on silver. So we can consider silver plus as a soft acidic center. So there will be a very good interaction between iodine and silver. Very good interaction, bonding interaction. Then CH3 IUG. When number of bond arising from any halogen is 2, then you need to put a positive charge on oxygen atom. You can calculate the formal charge, then you will see there will be 1 unit formal charge on iodine atom, on iodine. Okay, so CH3 Ag plus. So iodine wants to be neutral because iodine is electronegative. Okay, iodine is electronegative, so it wants to be neutral. So it becomes neutral after taking up this bonded electron pair. Then you will get CH3 plus and AgI. So now here a full positive charge, full 1 unit positive charge is present on carbon atom. But in this case, the partial positive charge is present on carbon atom. So that is why we consider this is soft acidic center. But I cannot consider carbon of CH3 plus as soft acidic center, as 1 unit full positive charge is present on carbon atom. So we can consider it as a hard acidic center. Now we have Cn minus, where carbon end is soft and nitrogen end is hard. So that is why we expect bonding between nitrogen and carbon, hard. And this reaction proceeds through SN1 because we are getting carbocation. Reaction proceeds through carbocation. So CH3 N plus C minus. So product is methyl isocyanate. But in case here product is methyl cyanide. Here it is methyl isocyanate. Okay. Very unique concept, and this reaction is very important in your syllabus. Okay, and here I have given you complete explanation, okay, about nucleophilicity, and that is enough for your IITJEE, for your NEET, or any competitive exam. Okay, so in my next video I will discuss about living group. Okay, so for today, bye.